Hi everybody, it's Miss Brenner here, and I am going to give you guys your first video lesson for this chapter, or this unit. It's your third video lesson altogether. So, you can open up your notebooks, and in your notebooks you can label this next part of your notes, electrons and light, because we are looking at, we're going to try to get some more information to answer that question from class on how do atoms create light. And so we're going to look at it in reverse today. We're going to look at what happens when we shine light into an atom and how does that affect an atom. And then we'll see if that'll help you reverse that and think about how does an atom actually produce light on its own. So we're going to first look at the electromagnetic spectrum. These are all the different forms of light that we can measure and that we're studying. And you guys should have seen this before. Hopefully you all remember the song from 8th grade on all of these different types of light. What I'm going to have you guys do first is pause me and draw your own wave that looks something like this wave. It doesn't have to be perfect, but big waves getting into small squishy waves, and then label all of our different types of electromagnetic energy or light energy on that little wave that you made. Cool. So now that you guys have done that, let's take a look at this. We know that there are these 7 different types of electromagnetic energy: radio, microwave, infrared, visible, ultraviolet, X-ray, and gamma, and they all look a little bit different. The reason that they're all different is because they're different sizes. The waves are actually different sizes. You can see over here, radio waves are pretty big. And when we actually measure how big they are, you can compare them to a house or a person. They're really, really large waves. They could be the length of a football field. So if you had the ability to see radio waves, you could dodge radio waves. You could be like, I don't know, a superhero. And then it goes all the way down to gamma rays, where they're so tiny. They're the size of a nuclei, right? The center of an atom. So these are super, super tiny. They're entering the atom, right? Because they're going past the electrons. They're smaller than that. Where X-rays are the size of an atom. So we have these wavelengths of all different sizes, and the size of that wave is really going to determine what that type of energy can do. Okay, so we'll start over here on the radio wave side. We use radio waves all the time for TVs, for cell phones, and they're really, really big waves. They have a big wavelength, right? So that would be something I would add on my diagram if I were you. And because they have a big wave, that means that they're low energy. Okay, it's the opposite of what you would think. They're the inverse of each other. A big wave is low energy, so the opposite. And then they also have a low frequency, meaning they're not going to pass by you as often because they're so big, right? It's going to take some time for that wave to actually pass by. And then on the other end, so as our waves start to get smaller and smaller and smaller, gamma waves are the opposite. They're the smallest wavelength, right? But they all, they have all the opposite characteristics. Small wavelengths mean that they're really high energy. So again, that's the opposite, the inverse of one another. They have high energy and a high frequency. There's a lot of waves passing by a given point over a certain amount of time because they're so small. Okay. So what we're going to look at is what happens if we shine or put any of these different types of light energy onto matter, onto atoms. What is it actually going to do to them? So here we go. How does energy actually interact with matter? So if I take any of these types of energy and shine them onto matter, what's going to happen? Radio waves are the first ones. We'll start big and we're going to get small. So the radio waves are so big that they don't even interact with matter. You could be getting hit with radio waves and they're just going to bounce off you, nothing's going to happen because they're really large. A lot of times they're missing you. This is how cell phones work, 5G and LTE. The reason that you can make a cell phone call and you don't hear other people is because you're all on a different wavelength, right? You're all on a different frequency. And as if you look back, go back here. Going from a building size to a grain of sugar, that's a lot of different wavelengths between there, right? There's a lot of different sizes of waves there. So we can assign my cell phone a wavelength size, and then I can talk to my mom, and you can get a different wavelength or a different frequency, and you can call your mom, and we won't interfere with one another. We're not going to hear each other. So that's how these cell phone towers are actually working. All right, and then microwaves. So we're getting a little bit bigger, or sorry, a little bit smaller, and these actually do something to matter. So they're going to hit the molecules, and a molecule is when you have two or more atoms together, bonded together. So you have like a couple different elements together, bonded, and they become a molecule, like water, right? H2O, that's a molecule. It's made up of more than one element, an atom put together. So what happens is in a microwave, or when you shine microwaves onto something, it gets those molecules to start spinning around, and as they're spinning around, it's allowing them to create heat, which in a microwave will heat up your food. So we're shining microwaves onto your food, and it really affects those water molecules, and those water molecules are spinning around and around and around, and then your food gets warmed up. If you put something without water in the microwave, it doesn't really do anything, because the size of that microwave is built to affect a water molecule. Next we have infrared. So infrared is when atoms, so not the molecule, but just a particular one atom, right, is getting hit, or it's going to affect just one atom. It's going to get that little atom to start vibrating, right? And so as it begins to shake, it's going to start to create heat, and that's why we use infrared to get those like heat pictures of things. Okay, so we went from molecules, or the whole molecule spinning around, to now just the little atoms are shaking in their spot. And then we get to visible light. So now we're getting to smaller wavelengths. The smaller wavelength, or smaller frequency, is going to be able to get to the smaller part of the atom. So now we're looking at electrons. Okay, so when atoms are hit by white light, that's all the colors, right? When you have white light, if you look at the sun, that's all the colors shining down on you. It allows the electrons, or it's enough energy to get the electrons to jump up energy levels. They're not going to leave the atom, but we know that there's like those rings around the atom, and it's going to get the little electrons are going to jump up to a different ring. And so they do that when they jump up. They're absorbing some of the colors, not all the colors, but some of them. And the colors that they don't absorb are the ones that you actually see. So, for example, if I'm looking at my green straw, all the colors are getting absorbed except for green. The green is being released. It's pretty cool. And then we have UV light. So UV, you think of that from the sun, right? You want to protect yourself from that because it's going to give you a sunburn. And why is that dangerous? Like, how is this light more dangerous than visible light, right? The sun also gives off visible light, but also gives off these wavelengths that are even smaller. And when those UV lights, ultraviolet lights, hit atoms, the electrons are not just jumping up, but they're leaving. They're ejecting from the atom itself. It's losing those electrons. And so if you lose electrons, you're going to become positively charged, and you become an ion, right? So if you lose something negative, you're becoming positive, and we're creating ions. And when we start to lose ions, ions are often, or are very important in creating bonds. So if you start to lose your electrons, you're not going to be able to create your bonds anymore. So it's actually going to break those molecules apart, right? Those molecules that are two or more atoms stuck together. And it slowly does that. And that's why when you go outside, you don't just immediately get sunburn, right? It takes some time for that UV light to start ejecting electrons. That's what's happening in your skin. It's breaking apart some of those bonds, and you're getting burned. And then X-ray is the same process. When atoms are getting hit with X-ray, it's just more energy. Those X-rays are smaller, they have more energy, and they're going to eject electrons the same way that they would in UV light, but it's just going to be a little bit quicker. So they're going to eject the electrons, they're going to create ions from that, and then again, if you lose your electrons, the electrons are needed to make bonds, you're going to break apart the molecules that those atoms have created. Right? So that's just going to happen at a little bit of a quicker rate because there's more energy, so more electrons are being released quicker. And then our final one is gamma. And gamma is the same thing again. that these atoms are getting hit with, oh, this should say gamma, I'll go change it, I'm so sorry, gamma light, the electrons are going to quickly be released. It's going to lose like a whole bunch of electrons at once. And when we lose a bunch of electrons at once, that can be really bad. That's why this type of light or radiation can be super dangerous to us, right? It can cause cancer. If you lose a lot of your electrons, you expose yourself to a bunch of gamma light, you're going to lose a bunch of electrons, and your body's just not going to have time to replenish them. And that's where we start to see problems. So same thing. That's happening just at a much quicker speed. So what I want you to think about real quick, as our little fun fact here, is we've learned about these gamma energy, right? That has to do with radioactivity and alpha and beta and gamma energy. And that energy that we're talking about was coming from the atom, right? It was coming from the nucleus when the nucleus was breaking apart. So we can see that we can affect an atom, or we can affect an atom by shining that gamma light on it and making it lose electrons, but it can also produce that energy itself. So how then can we get elements to produce all of these other types of energy? So I want you to think about that. How can it produce an X-ray or UV light or visible light or infrared light? So think about that, and you're good to go. Those are all of our notes. So when you have all this information placed in your notebook, then you can take a picture of it and submit it, turn it in on Google Classroom, so we make sure we check that off, because this is one of those learning activities that you have to do in order to be able to take the test at the end of the unit. So there you go.